Good morning, class. We are looking at section 4.2, the mean value theorem. We already covered section 4.1, maximum and minimum values. And so here's the synopsis of that. We looked at extrema, absolute extrema, as well as local extrema and what they mean in short. Absolute refers to the entire domain, and local means in an open interval inside the entire domain. And normally peaks and valleys will do the job. However, with the case of absolute, could be the endpoints. We looked at a critical point and what it means. Basically, any point that makes f prime 0 or does not exist is considered a critical point. The process involves 3 steps. Find f prime, set f prime equal to 0, also set f prime to does not exist or undefined, find it. Finally, we looked at the extreme value theorem or closed interval theorem. And the idea is that if you happen to have a continuous function and you have a closed interval of a to b, then the function must have an absolute max as well as absolute mean. And the process is very simple. Evaluate the function at the endpoints as well as the critical points. The largest value is the absolute max. The smallest value is the absolute mean. And now we're going to look at the mean value theorem, the section called the mean value theorem. So first we start with the Rolle's theorem. According to the Rolle's theorem, if we happen to have a function that is continuous in a closed interval of a to b, differentiable in the open interval of a to b. And if f of a happen to be equal to f of b, remember those are the endpoints, okay, a and b, then there is some number c in a, b such that f prime must be 0. Okay, and these are some graphs. Actually, a picture is worth 1,000 words, and pretty much they indicate that. But let's get us started with the concept. So this is the Rolle's theorem. The mean value theorem, okay, says if f is continuous on that closed interval of a to b and differentiable on the open interval of a to b, then there is a number c such that f prime equals to f of b minus f of a over b minus a. And as you may recall, this is the slope of a secant line, okay? So the idea is that if you have 2 points, okay, a and b, okay, class, connected, that creates what we call a secant line, okay? Look at some point between a and b such that there is a line parallel to secant line, which is a tangent line. Therefore, they must have equal slopes. Okay, class? This is a f of a, this is b f of b. And so f of b minus f of a over b minus a is the slope of the secant line, which happened to be the slope of a line parallel to that. So This represents the slope of a secant line. In other words, there is a point P where the tangent line is parallel to the secant line AB. Okay, class? The secant line AB, we are considering this line to be the secant line. And so the mean value theorem, in short, f is continuous, f is differentiable, there is a number c in between such that f prime is f of b minus f of a over b minus a. So that's the synopsis of it. Let's spend a couple of minutes quickly look at the proof of the concept class. So starting with the Rolle's theorem. So the Rolle's theorem indicates we have a continuous function, we have a differentiable function, and we know f of a equals f of b. All those three criteria are given. Therefore, there must be a point C such that f prime equals 0. So I want to make sure everyone understands what's going to happen. We know f is continuous. We know f is differentiable. And we know f of a equals f of b. Therefore, there must be a point C in between such that f prime must be 0. That's what the theorem is all about. So let's see how we can prove that. So quickly, the extreme value theorem, everybody remembers what the extreme value theorem says. The extreme value theorem says if you have a continuous function in a closed interval, okay, then it must have an absolute max as well as absolute mean. So let's assume alpha is where the max and mean occur. So f of alpha is the absolute max, f of beta is the absolute mean. So again, by the extreme EVT, short for the extreme value theorem, okay, or the closed interval theorem, this is going to happen. So case one, let's assume f of alpha equals f of beta. What does it mean? That means the max is equal to the mean. How can that be? It can only happen if you have a horizontal line. If you happen to have a horizontal line, pretty much you're done. Every point along the horizontal line has f prime equal to 0. So that's the end of the proof for case one. Okay. Now, what if they are not equal? Okay, if they are not equal and f of a is equal to f of b, right? Remember the third case. So if they are not equal, then they both cannot be the endpoints, okay? Just to give you an idea, okay, if you look at this one, the endpoint for this one, the endpoint for this one, okay? So this would be the, in this graph, absolute mean, and this would be absolute mean. Both of them are mean, but not that one of them is max. So if they are not equal, since f of a equals f of b, okay, then alpha and beta are not both endpoints. This is not class. So NOT, so this is okay. So that's the case. Now, so what does it mean? At least one of them must be in the interval of A to B, either the max or the mean. So one more time. F of alpha is not equal to f of beta. Since f of A equals f of B, alpha and beta are not both endpoints. Remember, f of A equals f of B, right? Okay, so at least one of them is in the interval of A to B, either the max or the mean. It doesn't matter, one of them. And f has a max or mean. Okay. Let's just write it here, class. F has a max or mean at this point. okay? And f is differentiable. We know that f is differentiable. How do we know that? Second criterion. So f prime of c therefore must exist according to this. And by Fermat's theorem, f prime must be 0. F prime must be 0 class, okay? All right, so that's the Rolle's theorem. Let's just look at a couple of examples of application of that. We want to find two x-intercepts of the function f of x equals x squared minus 3x plus 2 and show that f prime is 0 at some point between the two intercepts, okay, between the two intercepts, okay. And remember the Rolle's theorem. F is continuous on AB, F is differentiable on AB, f of A equals f of B. Now, obviously, when we find the intercepts, we have the third one. I hope you realize what the intercept is going to do. We're going to have two intercepts and f of those points are the same. And obviously, f is continuous and differentiable because it's a polynomial function. So, all right. So, f of x is x squared plus 3x plus 2. Factor it and you get 2 and 1, right? So x-intercept at 1, 0, 2, 0. So this is a basic elementary algebra. We do that, okay? So, all right, the function is continuous, the function is differentiable, and the reason being because it's a polynomial function. So Rolle's theorem applies. F is a polynomial. F is continuous from negative to positive infinity because it's a polynomial. Therefore, it's continuous from 1 to 2, closed interval of 1 to 2. F is differentiable on 1 and 2, okay, it's a polynomial, remember that. So also there are two roots. We prove that there are two roots, which means f of 1 equals f of 2. Okay, so we are looking at this one. So there is, this is an, there exists, okay, looks like the reverse E that reads, there exists a C such that f prime of C is 0, okay? So let's find f prime of C. Okay, so first of all, as far as the graph is concerned, it looks something like that. So f prime is 2x minus 3 set it equal to 0 and x becomes 3/2. Very straightforward class. I hope everybody's comfortable with that. And as you can see, 3/2 or 1.5 is somewhere in between, okay, between A and B. A and B, namely 1 and 2. Okay, here's the point, okay. Rolle's theorem is satisfied as there is a point at x equals 3/2 where f prime equals 0. I hope everybody's following what happened, okay. So a quick recap. All you have to do, look at the function. It's a polynomial function. So it's continuous differentiable everywhere, including 1 and 2. Why 1 and 2? Because the intercepts happen to be at 1 and 2. So the first one works, the second one works, and because there are two intercepts, the third one works. Okay, class? The third one works. Okay, and then you find f prime, you set it equal to 0. F prime, you set it equal to 0, and this number must be between 1 and 2, and you can see that. All right, we're going to do the same thing here. Basically, we're going to go through the same process. We want to find all C in the interval of negative to 2 such that f prime is 0. Obviously, again, we are dealing with a polynomial function. We are dealing with a polynomial function of degree 4. That means it's continuous and differentiable everywhere from negative to positive infinity. Okay. So the Rolle's theorem, the first part is working, continuous and differentiable, okay, from negative 2 to 2. Now, f of A equals f of B. Let's evaluate at negative 2 and 2. When we evaluate them, I hope you realize if you plug in negative 2 and 2, You have to show what it's equal to, okay? If you just say it's equal to 8, that's fine, as long as, you know, you've come up with that. So the first one works. The second one works simply because it's a polynomial of degree 4. Maybe instead of just writing polynomial, it's a polynomial of degree 4. So if you plug in -2, you get 8. If you plug in 2 equals 8. And the third criterion works. Therefore, there must be a C such that f prime must be 0. So let's find f prime, set it equal to 0. That's really the bottom line. So we showed the first 3 are there. Let's differentiate. So if we differentiate, we get 4x cubed minus 4x equals 0. This is a easy equation. Factoring will do the job. 4x times x squared minus 1. Okay. And we get those answers. By the way, I hope you realize x is 0. X squared equals 1, so x is plus minus 1. Or you can write 4x times x plus 1 times x minus 1 equals 0. Okay. So if we practically we are done with this. We have proved that. Okay. So in the interval of -2 to 2, the derivative is 0 at each of the following 3 points. By the way, you want the ones in between -2 and 2. All of them belong to the interval of -2 to 2. If you have a bunch and some are not, you just consider the ones that are in the interval of interest. So take a look at graphing this function. Again, you can use a graphing calculator. Okay. So we have those points. Okay, everybody. So that's a graph. So this is the case. Okay. By the way, it may appear like a corner. It's not. It's very smooth class. It's just that if you look at the different scale, you see it. All right. Again, Rolle's theorem is given at the top right for us to remember what it stands for. Okay. We want to use Rolle's theorem to prove that this equation has exactly one real root. So what we really need to do first, we have to show that it has at least one root. So there are 2 parts. One of them is finding roots, proving that there are roots, and then using the Rolle's theorem. To prove we have roots, we go with IVT. I hope you remember the intermediate value theorem. Okay, says there is at least one root. Okay, if we could figure out values such that this function is positive and -0 will be in between. And this is by inspection. So I want to make sure, you know, I remind everybody of what we are talking about here. Okay. So according to the IVT, okay, if you plug in a value to f of x and it gives you negative and for the roots in order to prove the roots, and one is positive. So some x value makes this expression negative, some make it positive. By IVT, if this is a continuous function in the interval of interest, it must have a root, okay, a 0 if you. Obviously, this is a polynomial of degree and it's continuous from negative to positive infinity. So because continuity is important, okay? So therefore, IVT applies. That's the first thing. If it's not continuous, it doesn't work, okay? Now, By inspection, you notice, obviously, for a negative number, the moment you plug in 0, you get negative. I hope you see that. So 0 gives you negative. But if you plug in 1 or 2 or 3 or 5, I hope you see that it quickly gives you positive. So again, this is by inspection class. So if you plug in 0, it results in negative value. And if you plug in basically any number, like 1 or larger, it gives you positive. Again, by IVT, okay, there is at least one root in between classes. I hope everybody can see that. Okay, I hope everybody can see what's going on. And so the IVT applies. Why is that? Because the continuous function from negative infinity to infinity, therefore it's continuous from 0 to 1. So in other words, now we are looking at the interval of 0 to 1, okay? Why 0 to 1? Because 0 gave you a negative value and 1 gave you a positive value, so from 0 to 1, okay? So I hope everybody understands what's going on, okay? And so having said that, we have proved by IVT, not the Rhodes theorem, that this function has at least one root, because IVT doesn't give you the number of roots. It just tells you there are roots in between 0 and 1. Now, we want to use the Rhodes theorem. So this is the first part. We just proved we do have roots. How many, we don't know yet. But if we use the Rhodes theorem, we are supposed to show that it has exactly one root. Okay? So that means we're going to use all these criteria. Of course, it's continuous and differentiable. Okay? But just to see what's happening, assuming it has two roots, then f of a is equal to f of b equals 0. Okay, so we are going to look at the Rhodes theorem in the interval of 0 to 1. Okay, suppose we have two roots. Then Rhodes theorem applies. So take a look. F is continuous. F is differentiable, polynomial of degree 3. If we assume they have two roots, then f of a becomes f of b becomes 0. Assuming that's the case, then there must be some point in between such that f prime is 0. So let's find f prime, set it equal to 0 and see what happens. So this must work, assuming those three criteria work. So let's take a derivative of f of x, and so f prime becomes what? 3x squared plus 1. Okay. So by Rhodes theorem, there is a C such that f prime equals 0. Let's find it. So when we find f prime, here's what happens. We get 3x squared plus 1. And this is always larger than or equal to 1. I hope everybody knows why. Because this is 3x squared. Worst case, this is 0. This is not only just larger than 0, it's always larger than 1, okay? So what does it mean? The Rhodes theorem fails. How can it fail? Let's see. Let's just investigate. We know f is continuous. Why is that? Polynomial. We know f is differentiable. Why is that? Polynomial. But this was our assumption, class. This is our assumption. If this assumption is true, okay, then there must be a point C that f prime is 0. We showed that there is no way for it to exist. Therefore, this assumption must be wrong. So this is by contradiction. F prime can't be 0. That's a contradiction. Since criterion 1 and 2, so the first one and the second one work. The first one and the second one, we can't change it. It's a polynomial. It will always work. Then number 3 is the one that we assumed. This must fail. So the equation can't have two real roots. And that's the idea behind this. Okay. I hope everybody's clear on that. Let's look at something fairly similar. We have a function f of x equals tan x. And we are going to show f of 0 equals f of pi. But there is no c such that f prime is 0, and y, it doesn't contradict this theorem that is called the Rolle's theorem. Okay. You really don't have to go even through the process, but let's go through the process. First of all, f of 0, tan of 0 is 0, f of pi, tan of pi is 0. I hope everybody knows that the tangent is 0 at 0 and pi. Okay. Now, take the derivative. F prime is secant squared, and that is larger than 0. I hope you remember the graph of secant. Okay. And basically the range excludes the numbers between -1 and 1. And so secant squared of x is larger than 0. Okay. So f prime of c can't be 0. Okay. And there is no solution. So the Rolle's theorem doesn't apply. But how come there is no contradiction? Well, a number of ways you can look at it. First of all, the function from 0 to pi is not continuous. I hope you remember the basic graph of a tangent. Okay. So this doesn't contradict Rolle's theorem since f prime of pi over 2 doesn't exist. Okay. And so f is not differentiable on 0 to pi. Also, f is not continuous on 0 to pi. In other words, let's see if we can. Okay. This is x equals pi over 2. X equals negative pi over 2. I hope everybody remembers the graph of tangent. The fact that it is not continuous from 0 to pi, because if you continue, by the way, this is one complete cycle. If you go to the next cycle, looks like this. Okay. So it's not continuous from 0 to pi. That's why. You don't even have to go with the rest of it. So it doesn't contradict the Rolle's theorem. All right. The mean value theorem was discussed. Okay. So the mean value theorem first stated by a French mathematician, Lagrange, the slope of a secant line, which is f of b minus f of a over b minus a. Okay. That means there is a point where the tangent line is parallel to the secant line. I can't really emphasize this. This is the meaning of the mean value theorem class. Okay. And by the way, Rolle's theorem is a special case of a mean value theorem, because if you look at the mean value theorem, notice the first one is the same, the second one is the same, but the third one is missing. I hope you see that. So adding the third one, f of a equals f of b, gives you the Rolle's theorem. So Rolle's theorem is a special case of the mean value theorem. Okay, so if we have a continuity and differentiability, then there must be a number in between such that f prime is equal to this. Okay, and by the way, I hope you realize if you do the cross product, okay, if you put a 1 underneath, it's the same as saying f of b minus f of a is f prime of c or times b minus a. That's the same thing. So let's quickly look at the proof. The proof is interesting to say the least. Okay, class. So at least you know you're not responsible for the proof, but at least if you're exposed to it once, it's not a bad idea. And again, as far as the graphs are concerned, class, When you connect these two, you see a line parallel to that and the C somewhere in between as far as the graph. If you look at this one, okay, if you connect A and B, that creates the secant line. There happen to be 2 points where the lines are, the tangent lines at C1 and C2 are parallel. So uh, the mean value theorem is just an extension of Rhodes theorem, or more importantly, Rhodes theorem is a special case of a mean value theorem. Take a look at the third criterion that the mean value theorem does it. So what we are going to do, we just need a function that satisfies Rhodes theorem, okay? So remember, we have a continuity and differentiability, okay, for the function f of x. Now we are going to introduce a new function h of x, where is the difference between f of x and g of x is the equation of a secant line. In other words, if this is the function class, this is the function f of x, okay, then this line, the blue line, is the secant line. So the difference between this function and this function, we give it the name h of x. Now this function is f of x, is not a big deal. But what is this function? This is a secant line, everybody. Can we come up with the equation of a secant line? Yes. We have two pairs. We come up with the slope, and y minus y1 equals m times x minus x sub 1. So let us write the equation for the secant line, and we're going to call it g of x. So let's see how it works. Okay, we are going to go with y minus y1 equals m times x minus x sub 1. And remember what's y sub 1. Pick one of those, okay? So in this case, the first one would be f of a, so y minus f of a. And what is m? Remember that m is what? F of b minus f of a over b minus a. I hope you see that this line, the slope, we can calculate it as such. X minus x of 1, x minus a. I hope everybody can see that this is nothing but the point slope. Okay. Therefore, y or g of x is this right side, and move minus f of a, make it plus f of a on the other side. So y or g of x is just moving f of a. This is it. Now we are going to come up with h of x, which is f of x minus g of x. So f of x minus g of x. What was g of x? This thing. That means minus f of a minus this. I hope you see that we are just doing a basic elementary algebra, subtracting g of x from f of x. Okay. Now, we know g is differentiable. First of all, it's a linear function. Secondly, just differentiate it. What if I differentiate? Take a look at this function. If I want to differentiate, f of a is a number, 0. This one is a coefficient times x minus a. So this one times the derivative of the parentheses, which is 1. So I hope you see that if you differentiate g of x, it results in f of b minus f of a over b minus a. I hope everybody can see that. Okay. Now, what about h prime of x? H prime of x is f prime of x minus g prime of x. F prime of x minus this one. Okay. So now, why have we done this? So Rolle's theorem applies to this h function class. H is a continuous function. It's differentiable function. Okay. And if you plug in a, I hope you realize if you plug in a, okay, we replace the x with a, everything cancels out, we get 0. If you change it with b, you end up with 0 also. So take a look at what happens. First, h is continuous. Then h is differentiable. Why is that? Because h is the difference function for f of x, which was a continuous and differentiable function, and g of x, which we proved it's differentiable and continuous, or just a line, a continuous function minus a line. So it is still continuous, it is still differentiable. Now h of a, again, I want you to try this on your own. Plug in a and evaluate. This becomes 0. Plug in b, okay, you get f of b minus f of a, minus f of b minus f of a over b minus a, and these two cancel each other. These two with negative, they cancel each other. So I hope you can verify this. I leave it for you to verify. Plug in. Therefore, the Rolle's theorem apply, and if the Rolle's theorem apply, there is a place where f prime is 0. Okay, so therefore, in this case, the function was h. H prime is 0, everybody. H is this. H prime is this. So if h prime is 0, that means f prime minus f of b minus f of a over b minus a is 0. That means f prime of x equals f of b minus f of a over b minus a, okay, at some point c. I hope you see that when you set this one equal to 0, you're setting this one equal to 0, and it results in this one when the choice is c. Believe it or not, this is the proof of the mean value theorem, and as it was mentioned, Rolle's theorem is a special case of a mean value theorem, everybody. Okay, let's look at some examples of that. The mean value theorem we're going to use here. If the function given is 5 minus 4 over x, we want to find all c in this interval such that the slope of a secant line equals the slope of a tangent line, meaning this one. Okay. Now, the first thing you notice is here's the rough sketch of that point. Okay. We are looking for that. That's the idea. And by the way, that's portion of a graph. That's not the whole graph, class. Okay. So I hope you realize that this function is continuous everywhere except at x equals 0. Same thing, differentiable everywhere except at x equals 0. And when you look at this one, it doesn't contain 0, so we are good to go. F is continuous and differentiable from 1 to 4. Why is that? I want to make sure everybody understands why. This is a rational function, and domain is all real numbers except 0. Because of that, in other words, minus infinity 0, union 0 to infinity. So from 1 to 4, we are in good shape. We have nothing to worry about. So what do we have to do next? Very simple. Okay, we are going to say f prime of c equals to this. So we have to differentiate this on the one hand. On the other hand, we have to calculate this, and we set them equal, where the point A is 1, the point B is 4. Okay, so I hope you realize what we are going to say. F of 4 minus f of 1 equal over 4 minus 1. That's the right side. And then f prime differentiated, set them equal. See how easy we can come up with the answer. Okay, so f of 4, if you plug in, you get 4 over 4 or 1, 5 minus that, it's 4. Okay, and f of 1 would be 1, so this is 1. So you differentiate 5 minus 4 over x, or simply 5 minus 4x to the power of negative 1, and it becomes 4 over x squared. I hope everybody is comfortable with that. Maybe I'll quickly show you that one too. F of x is 5 minus 4x to the power of negative 1. F prime is minus 4 times minus 1 x to the power of minus 2. and that's 4 over x squared. So set this equal to 1, solve for x. So x squared equals 4, x is plus minus 2. There are two answers, but take a look at the restriction that we have. We go from 1 to 4. Which one is in between? Only positive 2. So you can't have both of them. I want everybody to realize why not. There are two answers, but in the interval that we are interested in, only number 2 works. So that's another thing you want to be careful when you answer questions like this. Whatever is in the interval, that works. Anything outside does not. Okay. Okay. So f of x is x cubed minus x, and we're going to go from 0 to 2, a and b. Okay. So illustrate the mean value theorem. That means, okay, look at number 1, is it continuous? Number 2, is it differentiable? Okay, the function is a polynomial of degree 3 or cube function. Therefore, it is continuous from 0 to 2, the closed interval of 0 to 2, and differentiable in the open interval of 0 to 2. So we need to find f prime, which is 3x squared minus 1. And then we need to find f of, the bottom line is find the left side, f prime of x. And the right side of this equation class, f of b minus f of a over b minus a, and set them equal. Okay, so that's really the idea. So continuous and differentiable, I've mentioned why. It's a polynomial of degree 3. Polynomial of degree 3. Okay, so that's why. Okay. So the mean value theorem applies. Okay. By the way, whether you write it in this form or this form, it doesn't matter to me. Okay. Most of the time, I think it's easier to remember this because it's simply what? The slope. Okay. The slope of a secant line. So I think it's a tad easier, but it's the same thing if you do the cross product. In any event, so you calculate this by going through this. I'm assuming everybody can plug in 2. Okay. So 2 cubed, 8 minus 2 is 6. 0 gives you 0, and so the answer is 3. So find the derivative, which is what? 3x squared minus 1, set it equal to 3. So 3x squared equals 4. X squared equals 4/3. X squared is plus minus square root of 4/3. There are two answers, plus minus, but what do we want? Interval of 0 to 2. So the negative is out. In the interval of 0 to 2, the negative is out, everybody. So only one choice, x equals 2 over square root of 3. Okay. Do you have to rationalize it and write it as 2 square root of 3 over 3? It's not a big deal, okay? But you graph this, okay? Looks something like this. All right, looks something like this. Y equals x cubed minus x. And the tangent line at x equals 2 over square root of 3 is parallel to the secant line OB. Okay. Remember, we are going from 0 to 2. This is 0, 0. This is 2, 6. Okay, just in case. Okay, and this is the other point, the origin. All right, so to recap, if you're illustrating the mean value theorem, what do you do? First, you show continuity, then you show differentiability. Okay. And then you find f prime of x. Then you find f of b minus f of a over b minus a, set them equal. And that becomes a value of c when you set them equal and solve. Okay, that's how the process works. All right. Again, here we're going to use the mean value theorem to do this. Suppose f of 0 is given, and it's -3. And we know f prime is less than or equal to 5. That means f prime of x is less than or equal to 5 always, okay? How large can f of 2 possibly be? Okay. All right. So here's a solution. If we look at the mean value theorem, this function is continuous and differentiable in the interval of a to b. First of all, what is a? 0. What is b? 2. I hope you realize. So a and b, we need to know what they are. Then how do we know they are continuous and differentiable? Well, if a function, if it says f prime is less than or equal to 5, that means it's differentiable. And if it is differentiable, it must be continuous, not the other way around. I hope you remember that. Any function which is differentiable, it is also continuous. Therefore, we have the first two. Okay. So why is this? So start with this. Why is this differentiable? It says so. Over here, it says f prime is less than or equal to 5. That's why. If it is differentiable, it's always continuous, class. Okay. As long as you have differentiability, you have continuity, but not the other way around. So far, so good. How do we do this one? Okay. We need the left side and we need the right side, or we can look at the bottom, f of b minus f of a. Okay. Remember, you go from 0 to 2. So you have f of b, you have f of a, okay, f prime of c times b minus a. So why don't we put it in that context, knowing that f prime is less than or equal to 5. That means f prime of any point, including c, is less than or equal to 5. So let's put that, okay. The mean value theorem applies. We know f prime is less than or equal to 5. Therefore what? Therefore, if I write this one, f of b minus f of a over b minus a, or I write this one, it doesn't. If I write the right side of this, must be less than or equal to 5. I hope you realize that. So one more time. Because f prime is less than or equal to 5, and because f prime equals f of b minus f of a over b minus a, then this expression must be less than or equal to 5. So what is f of a b? Okay. I don't know. F of 2. What is minus f of a? Minus -3. And then 2 minus. I hope you see what I'm doing. I'm just using this one. Everything is there except f of 2. Okay. So we plug in and we do the cross product. Okay. We can multiply both sides by 2, right, class? This goes away. This becomes 10. Subtract 3. And the answer is 7. So I hope everybody can see how we arrive at this answer. Okay, everybody, any questions? I think it's pretty straightforward. Okay, so let's quickly recap. F of 0 is known. F prime is known to be less than or equal to 5. And we are interested in finding f of 2. Okay, because f prime is less than or equal to 5, we don't have any problem with the continuity and differentiability. Then we use the fact f prime is less than or equal to 5, and we say f prime of c, which is f of b minus f of a over b minus a, is less than or equal to 5, and therefore everything else follows. Okay, I hope we are okay with this. Okay. Suppose f prime is between these two numbers. We want to know this is the case. We want to show that. Using the mean value theorem in essence. By the way, if it's in that section, it's clear we want to use the mean value theorem. If it's not, we may not know that, okay? So we want to be careful with the concept. So we are using the mean value theorem to show that's the case. So the mean value theorem, see if it applies or not. Number one, f is continuous, okay? Number two, f is differentiable on a to b. Okay, first of all, what is a to b? We are looking at f of 8 minus f of 2 here. So it must be from 2 to 8. So that's a and b. Then, is it true that they are continuous and differentiable? Yes. How do we know that? A very fair sentence says f prime is between 3 and 5. That means f prime is always there, and the numerical value is between 3 and 5. So this statement tells us f prime does exist. So if a function is differentiable, then it must be continuous. In fact, it says the derivative is always between 3 and 5 in the entire domain. Okay, we may not know what the entire domain is, but it works from 2 to 8. All right, so again, we go through the same process as the previous page. We are going to basically go with this or that because the first two work. So let's write them down. F is continuous and f is differentiable from 2 to 8. This is closed, this is open, and simply because of this statement, I can't emphasize the importance of this statement that says the function is differentiable everywhere. Therefore, it's continuous. So the mean value theorem applies. Okay. Now, let's go with this statement. F prime is between 3 and 5, everybody. Okay. So let's write it. F prime is between 3 and 5. So let's start with that. F prime is between 3 and 5 for all x. Okay. So if f prime is between 3 and 5, that means f prime of c equals f of b minus f of a over b minus a must be between 3 and 5. Okay. That must be the case. Okay. So just replace the a and b. A is 2, b is 8. So f of 8 minus f of 2 over 8 minus 2. Let's do that. So what is 8 minus 2? Number 6. Because it's a positive value, when you multiply all sides of equality, it stays intact. So I'm going to multiply this one by 6. I get 18. This one I get 30. And so this is the proof that f of 8 minus f of 2 is somewhere between 18 and 30 inclusively.